Welcome to lesson 6.1, where our goal is to understand exponents. Now I know that you've used exponents before, but I really want to break this down so that you understand what exponents are and you can understand them without using a calculator. To get started, we're going to take a step back and talk about repeated addition. When we have repeated addition, we can rewrite it as multiplication. Here's an example. Let's say I have the number 4 and I want to add 4 to itself, and then I want to add another 4, and I could add however many 4s I want. I'm just going to use 3. So 4 plus 4 plus 4 is an addition problem that I can do, but I can also rewrite that as 3 times 4. Repeated addition of the same number can be rewritten as multiplication. 4 plus 4 is 8, and 8 plus 4 is 12. And also, if I multiply 3 times 4, I get 12. Now let's take that idea to understand exponents. If instead of repeated addition, I have repeated multiplication, I can rewrite that as exponents. So I'll just use the number 4 again, but this time I'm going to be multiplying. 4 times 4 times 4. I can rewrite that as 4 raised to the third power. The 3 is a power or an exponent, and 4 is the base or the number that I'm using as a factor. If I look at the left side of this equation, 4 times 4 is 16, and 16 times 4 is 64. And if I take 4 to the third power to my calculator, then it's going to give me 64 for that as well. So exponents are just a shortcut notation for repeated multiplication. Now go back to the first example in your notes. The position of each number when you have exponents is very important. The exponent needs to be raised and to the right of the base. That way there's no misunderstanding about whether it's an exponent or if it's multiplied by the 7. But if I have 7 raised to the third power, then that's the same thing as 7 multiplied by 7 multiplied by 7. These numbers can get really big or really small very quickly. If we need to use a calculator to evaluate those, then we can do that. So one way I can do this is just type it in, 7 times 7 times 7, and I get that answer. But if my exponent is very large, I certainly don't want to do that, so I can write 7 raised to the, so you see my little caret with the red button right there, raised to the third power, and I get the same answer. Now, if you want that little caret on your keyboard, then Shift 6 to get that. While we're here, let's talk about what it is not. If you have 7 raised to the third power, that means 7 is used as a factor 3 times. It does not mean that you multiply the exponent times the base. Okay, 7 times 3 is equal to 21, and clearly that is not equal to 343. So I see that mistake a lot. Don't make it. In the next example, we have 7 raised to the 0 power, which according to our definition means that we're supposed to take our base 7 and use it as a factor 0 times, which means that we're not using it as a factor. So what do we do with this? We can't just make up a number that this is equivalent to. Let's go back to our first example. There's a number in multiplication that if I use and I multiply it by something, then it doesn't change it. That number is 1. A lot of times we don't write the 1. We just assume it's always there. It's kind of invisible, right? We write it if we need it, and we don't write it if we don't need it. So we can use this understood 1 right here and say, well, 1 is always a factor, and then 7 is not used as a factor at all if we have 7 to the 0 power. So the only thing remaining is that factor of 1. Any number to the 0 power is equal to 1. There are 2 exceptions to that rule, and we will talk about those in a minute. Now, the most common misconception on this example is to say that 7 to the 0 power is equal to 0. It is not equal to 0. In the next example, we have a variable x as our base, but that doesn't change the definition of exponents. If I have x raised to the 7th power, that just means that I want to use x as a factor 7 times. Remember that when we write variables next to each other, that implies that they're multiplied together. So as long as I have 7 x's right there, that means they're multiplied together. Now, I don't know what that number is because I don't know what value x has. If I have a variable raised to the 0 power, then that's going to equal 1 for the reasons that we talked about up here. 7 to the 0 power is 1. Now, here's where those exceptions come in. X cannot be 0, and x cannot be 1. But any other number x to the 0 is equal to 1. Exponents will be used in combination with other operations, so we need to review those operations. Addition and subtraction are the very basic operations that we do. If we have repeated addition or repeated subtraction, then we can rewrite those as multiplication or division expressions. And as we just discussed, if we have repeated multiplication, and as we will discuss later, repeated division, then we can rewrite that as exponents. And then parentheses or any kind of grouping is above that. Now if we're evaluating, then we're going to start from the top down. In our example, 2 times x to the 7th power is already in its simplified form, but we could use rules for exponents or the definition of exponents to write that in another form to make it understandable. Here the 7 only applies to the x because the x is not grouped with the 2. So we have 2, which is a coefficient that's just multiplied by x to the 7th power, which is 7 factors of x. Again, let's talk about what this is not. A common mistake would say, well, that power of 7 goes to the 2 and the x, so maybe we have 2x used as a factor 7 times. But if you had 2x used as a factor 7 times, then you would have to group those two factors together and then raise that group to the 7th power. So that is not for all numbers the same thing as 2x to the 7th. The next example is just to show you that our base can be a number like 7 and our power can be a variable. So 7 to the x is a valid expression. We're not going to work with those in this lesson. Maybe later in the unit we'll talk about those some. Don't be pranked when you're working with exponents. There are some mistakes that are made so frequently that I just have to point them out to you so that you won't be pranked when they come up. Here's the first one. If I have -3 squared, and this is just an example, you could substitute any numbers there, that's not going to be equal to the parentheses -3 squared. In the first example, we have -1 multiplied by 3 squared, which is 3 times 3, which gives us -9. On the second example, we have -3, the negative and the 3 used as a factor twice. So -3 times -3 is a +9, and -9 and +9 are not equal to each other. So that's probably the most common mistake. Here's another one. If you have 4 to the 2nd power, and we talked about this already, that's not the same thing as 4 multiplied by 2. 4 to the 2nd power means 4 is used as a factor twice, which is 16, and 4 times 2 is 8, and those are not equal to each other. One more example. If I have 5 raised to the 3rd power, that's not the same thing as 3 raised to the 5th power. In other words, exponents are not commutative. You can't just change the places of them. And we'll go to the calculator to prove this one. So if I raise 5 to the 3rd power, I get 125. If I raise 3 to the 5th power, you see I get 243. So two different numbers. Let's use the definition of exponents to really show our work on these next 4 examples. Now I know that you can type these in the calculator because it's all numbers, but that's not what's important here. What you need to do is understand how these exponent expressions can be rewritten so that you understand what's happening. In the first example, I have a fraction for my base, but that doesn't change the definition of exponents. I just want to take that base of 1/3 and use it as a factor 4 times. So I could rewrite this as 1/3 times 1/3 times 1/3 times 1/3. Now when we multiply fractions together, we multiply the numerators. 1 times 1 times 1 times 1 is 1. And we multiply the denominators. So 3 times 3 is 9, 9 times 3 is 27, and 27 times 3 is 81. Feel free to check that in your calculator, but do not give a decimal answer, and make sure that you understand the definition of exponents. Let's look at the other example. We have multiplication, 2 times -5 to the 2nd power. Now a common mistake is to multiply the 2 times -5, but you can't do that because the order of operations tell us that exponents have to come first when we're evaluating, have to come before the multiply or divide. So first let's rewrite our exponents. Negative 5 to the second power is negative 5 times negative 5. Now that these are all factors, we can multiply them in any order. So we get 50. In the next problem, we have 3 to the 0, which we know is 1, plus 2 to the 5th power. So 2 is used as a factor 5 times. And I want you to write it out like that. If I multiply, because I have to multiply before I add, 2 as a factor 5 times is going to be 32. And then I'm going to add that 1. My final answer is going to be 33. In our last example, we have a grouping 3 times 4, and then that's raised to the 3rd power. The 3rd power applies to the whole group. Let's simplify inside the group first. 3 times 4 is 12, so 12 is raised to the 3rd power. So I have 12 used as a factor 3 times. And 12 times 12 times 12 is 1,728. Turn your paper over and let's see what happens when exponents are fractions. Again, we're going to back up and start with repeated addition, and then we'll get to the exponent part of it. So if I have 3 times 16 and I want to rewrite that as repeated addition, then I have 16 plus 16 plus 16. Now what happens, instead of multiplying a positive integer like 3 by 16, I want to multiply this fraction, 3/4 times 16. And I want to keep that idea of repeated addition. So what I need to do is take my 16, and I want to come up with 4 blanks. And the number in each of these blanks, or each of these terms, needs to be the same number. But when I add those numbers together, I should get 16. So I could guess and check a little bit, but 4 plus 4 is 8, 8 plus 4 is 12, and 12 plus 4 is 16. Now the fraction that I'm dealing with is 3/4. 4 is the whole thing. Okay, that's the whole thing divided into 4 parts. I only want 3 of those parts. So I just want these 3 terms right here. 4 plus 4 plus 4 is the same as 3 times 4, or 12. Now let's shift to repeated multiplication and understand how that will apply to exponents. If I have 16 to the 3rd power, then that means I have 3 factors of 16. But what if I don't have complete factors of 16? I want 16 raised to a fractional power. Again, I'm going to look at the bottom of that fraction. That's how many parts in my whole. So I want to take 16, and this time instead of addition, I want 4 factors, and they need to be the same number as each factor. When I multiply them together, I need to get 16. 4 is too big, because when I added 4 times, I got 16. Let's try a smaller number. Let's try 2. 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. Now I don't want all 4 of those factors. I want 3 of the 4 factors. So I'll take these 3. Since they're factors, I can write them 2 to the 3rd power, or I can multiply it out and get 8. So 16 to the 3/4 power is 8. Let's look at some more examples just to see that again. Let's raise 8 to the 2/3 power. So over here I'm going to look at 8, and I want to find 3 factors, same number for each factor, and I know I want 3 because that's the bottom number of my fraction, and that represents how many parts in the whole thing. So if I multiply 2 times 2 times 2, then I get 8. But I don't want all 3 factors. I want 2 of the 3 factors. So if I just choose 2 of those, then that's 2 squared, or I can simplify to 4. Again, I know this is something that you can just type into your calculator and get the answer, but once we introduce variables into this type of thinking, you're not going to be able to just type those in. So take the time to understand this right now. Here's another example, 32 to the 3/5. So I want to take my base of 32 and I want 5 of the same factor. Why do I want 5? Because that's the bottom number of my fraction, which represents the whole of 32. I know it has to be a small number. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is 32. So even though the numbers start small, they get big very quickly when you are multiplying them together. Now, how many of those factors do I want? I look at the top number. I want 3 of them. And 2 to the 3rd power is equal to 8. This works even if our fractional exponent is improper. In other words, the numerator is larger than the denominator. So let's take our base of 27. We're raising 27 to the 4/3 power. So the bottom number tells me how many parts are in my whole. So I want 3 factors, same number, multiplied 3 times, and I get 27. I know it's not 2. Let's try 3. 3 times 3 is 9. 9 times 3 is 27. So 3 is the base that I want to use, but I want to look at the top number over here to tell me how many times I want to use that. So I want to use it 4 times. And I know 3 to the 3rd power is 27, so maybe I'll write it this way. I want all of those, and then I want another factor of 3, because I want 4 factors of 3 altogether. So that's going to be 27 times 3, which is 81. And here's our last example, 36 to the 3/2 power. Again, I have that improper fraction, but I'm going to take the base of 36, and I want 2 factors, same number, used twice. So what do I multiply by itself, and I get 36? Well, that's got to be 6 times 6. These always have to be the same number. So how many do I want? I want 3 of those. So I want 6 to the 3rd power. Or I want 6 to the 2nd power and then another factor of 6, which would be the same as 6 to the 3rd power, or 36 times 6. When I look at your work, I want to see it broken down like this. I don't want just numbers for the answers on your practice. And your practice is next, so let me know if you have any questions at all. I'm happy to help you.